Hello, and welcome to Sleepy Scientist. I'm glad you're here, whether you've had a long day, a busy mind, or you simply love falling asleep to the sound of science. Tonight, we're going to drift together through one of the most mysterious and invisible dramas. Our planet ever stages the slow dance of a magnetic pole reversal. You and I will walk through skies lit in strange colors, fields humming with unseen change, and rocks quietly etching a message into deep time. As you listen, I invite you to imagine yourself moving through these scenes in the present tense, because in a way, the Earth's magnetic field is always in motion, and we, its passengers, are part of the ride. Before we begin, I'd love to know, where in the world are you listening from right now, and what time is it there? Leave a little note if you feel cozy enough. If you enjoy these sleepy explorations, I'd be so grateful if you gave the video a little like and tap that subscribe button. It helps more sleepy scientists like you find their way here, and it means I can keep making more of these journeys for you now. You feel it before you see it, an almost imperceptible shift, as if the invisible shell that cradles the Earth is breathing differently tonight. The magnetic field, our planet's silent guardian, usually stretches from the southern hemisphere to the north, in great arcs of charged particles steady and sure. But now, in ways no naked eye can see, it begins to wander. Imagine an invisible wind that's always flowed from one direction, suddenly curling, hesitating, changing its mind. That's the feeling in the air, a restlessness in the compass of the Earth itself. Above you, though nothing yet disturbs the stars, a delicate stirring begins in the upper atmosphere. Charged particles that normally slide along well-worn magnetic highways start to stray onto side streets. The Earth's magnetic poles, those deep anchors of invisible force, are shifting. They do this not out of malice or whimsy, but as part of the restless churn of molten metal in the planet's outer core. Down there, 3,000 kilometers beneath your feet, liquid iron swirls and folds like thick soup in a cauldron, generating electrical currents that breathe life into the field. But sometimes these currents twist into new patterns, like a dancer changing steps mid-performance. If you could hover in space and watch the field lines, you'd see them bending, curving in new ways, perhaps bunching like tangled threads on one side while loosening on the other. The North Magnetic Pole, somewhere in the high Canadian Arctic, drifts faster than it ever did in centuries past. Scientists on the surface note its speed increasing from about 10 kilometers a year to more than 50. South's twin is shifting too, a mirror in motion. You might ask yourself, how do you notice something that is invisible? Would you feel a tug in your bones, a whisper in your inner ear? Or would you only see the clues in what the field touches? Compasses migrating animals, the pale lights of the aurora. You wonder how early humans might have felt such a change with no tools but their senses. The shift is still subtle. If you stand in a meadow and hold a compass, the needle still points roughly north, but there's a slight quiver, as if it is beginning to doubt itself. Birds flying overhead navigate with ancient instincts, sensing the magnetic lines like invisible rivers in the sky, but perhaps some already take a wrong turn. This is how a reversal begins, not with an explosion, but a murmur. The field's strength, usually around 60 microteslas near the equator and higher near the poles, has started to wane in certain spots over South America and the southern Atlantic. Scientists track a growing weak patch called the South Atlantic Anomaly, a place where the magnetic shield is thinner, letting more cosmic particles brush the upper atmosphere. Picture Earth as a great glowing lantern in the dark, wrapped in a shimmering bubble. That bubble, the magnetosphere, is shifting, reshaping. If you close your eyes, you can almost hear the field's lines singing differently, their tones bending in ways your ears can't quite catch. It's the sound of change, and though it takes thousands of years for a full reversal, you are already walking in the first steps of the dance. And somewhere in your mind, a quiet question lingers. If the Earth's magnetic field is our shield, what stories does it whisper when it starts to change? You lift your eyes to the horizon, expecting the usual velvet black of night or the gentle gradient of dawn. But instead, the sky is painted with a curtain of shifting light, and you're nowhere near the poles. It begins faintly like watercolor washed thin across the stars. A soft green haze pulses just above the tree line, slow and rhythmic, as though the sky itself is breathing. The green deepens, tinged with crimson at the edges, and soon whole ribbons of light ripple overhead. These are auroras, yes, but not the kind you've known. They are far from their ancestral homes in the high latitudes. Here in a place where auroras were once rare or impossible, the magnetic shift has drawn them down like migrating rivers of light. The cause hides in the invisible ballet above your head. Normally, Earth's magnetic poles funnel charged particles from the sun toward the polar regions, where they slam into atmospheric gases and set the sky alight. But as the poles wander, those pathways twist, bending over lands and seas far from their usual latitudes. The auroras, like dancers given a new stage, find themselves spilling across unfamiliar towns and fields. Imagine living in the tropics and seeing your first aurora, the air warm and scented with night-blooming flowers, while the heavens above churn with cold green fire. Perhaps children would giggle in the streets, running barefoot under the glow. Farmers might pause in their fields, leaning on their tools to watch the silent performance. And maybe somewhere far away, a poet would write about emerald rain falling upward. The spectacle hides a deeper truth. These lights are not just beauty, they are evidence. Charged solar particles, guided by a rerouting magnetic field, are touching places they haven't touched in many millennia. Where the field is weaker, more of them get through, striking oxygen and nitrogen molecules at unusual latitudes. Oxygen at high altitudes glows green or red, nitrogen purplish and pink. Together they weave tapestries that hang across continents. You might ask yourself, if auroras can wander so far, what other invisible patterns are changing above you? Could the very color palette of the planet shift for centuries at a time? And if the magnetic field weakens more, would these lights one day be visible from nearly anywhere, turning Earth into a world with a nightly planetary show? Scientists, of course, would be busy measuring the phenomenon. They'd record auroral oval maps, stretching like elastic bands toward the equator. Instruments on satellites would hum with new data, particle densities, energy levels, latitudinal spread. A researcher might smile at the thought that in ancient pole reversals, humans, or even earlier creatures, may have stood under skies like this, their memories lost, except for the traces etched in myths of fire in the heavens. But for you standing here now, the science blends with the sensory. The lights ripple like silk caught in an invisible breeze. They dance silently, but the silence feels heavy, as though the earth is holding its breath. The stars shine through the auroras, dimmed and refracted like lanterns seen through gauze. Hours pass without you noticing. The sky seems to have its own slow heartbeat, pulsing colors that drift and fade then return. At times, faint spirals appear, green, winding into violet, then vanishing as though embarrassed. Other times, a curtain of red descends almost to the horizon, like the closing act of a play you didn't know you were attending. Even after the auroras fade, a ghost of light remains in your memory, etched as clearly as any sunrise. The night seems deeper now, and you sense perhaps for the first time that the poles are not fixed anchors, but wandering actors in Earth's endless drama. And somewhere in the quiet, you wonder if the sky can change this much when the poles wander. How will the rest of the world follow? The next morning, you notice the change in something far smaller than the sky. You take a compass from your pocket, a little silver case, its needle steady for as long as you've owned it, and watch as it twitches almost imperceptibly. It's subtle like a cat flicking its tail in its sleep, but it's there. You turn slowly in a circle, letting the needle swing, and instead of settling with its usual quiet confidence, it wavers like it's unsure of where home is. Normally, a compass is a simple, stubborn thing. It points to magnetic north, the invisible pull of the planet's molten heart. But today it feels more like a gossip who's heard too many rumors at once and doesn't know which story to believe. For centuries, sailors trusted that tiny arrow to guide them across vast oceans. Explorers carried it through forests where every tree looked the same. Pilots once used it as a backup when the stars were hidden by clouds. It's been a quiet partner in every journey you can imagine. And now, during this great magnetic drift, it has started to lose its steady voice. Deep beneath your feet, the molten iron of Earth's outer core swirls like a vast, slow ocean. Those currents generate the magnetic field, but the currents are shifting, folding in on themselves, reversing in places. The north and south magnetic poles aren't fixed points at all. They're more like wandering spirits, sometimes drifting slowly, sometimes racing ahead. Right now, they're moving faster than they have in recorded history. You might ask yourself, what happens to a world when its compass lies? Would explorers of the past have found their way if their tools pointed somewhere else entirely? And what will it mean for navigation today when airplanes, ships, and even smartphones rely on that invisible thread to orient themselves? The truth is, most modern navigation leans heavily on GPS satellites, which don't care about the planet's magnetic whims. But compasses still matter in wilderness travel, in military operations, in survival. And for many species on Earth, from sea turtles to salmon, the magnetic field is the only map they have. You imagine a future museum exhibit titled, "When Compasses Went Wild." Inside would be a display case holding dozens of compasses, their needles frozen mid-swing, captured during the reversal. Panels would explain how in this period, north might have been east for a decade, or how local magnetic anomalies made navigation a guessing game. Even now, surveyors, pilots, and mariners update their magnetic declination charts more often because the old ones expire like milk left in the sun. The World Magnetic Model, the official global map of magnetic north, used to be revised every 5 years. During rapid drift, it might need correction in less than 2. Imagine telling a sailor in the 1700s that their charts could go stale so quickly. You stand there a while longer, watching the needle's small, restless motions. It seems alive somehow, like it knows a secret you don't. And, in a way, it does. The compass isn't broken, it's telling you the truth. The ground beneath your feet is steady, but the invisible lines wrapping around the Earth are not. Somewhere far to the north, the magnetic pole edges another kilometer along its wandering path. And somewhere deep below, the liquid heart of the planet stirs again, a reminder that even the most ancient-seeming things are always in motion. You don't feel it on your skin, but the shield above you, the great invisible dome of Earth's magnetosphere, is shifting like a restless dream. Normally, it's a smooth, rounded bubble, deflecting most of the sun's charged particles before they can brush the atmosphere. But tonight, in the silent space beyond your sight, that shield is wrinkling and thinning in places like fabric stretched too far. If you could see it from orbit, you'd notice the magnetosphere bowing inward on the side facing the sun, while the far side stretches into a long tail that snakes away into the black. That tail flutters more than usual now. Charged particles slip through gaps they once couldn't, gliding along new magnetic lines toward the atmosphere. The cause lies deep beneath your feet in the molten iron currents of the outer core. As those currents change direction and strength, the magnetic field they generate loses its perfect symmetry. The once strong shield becomes patchy, not gone, but less certain. And you might ask yourself, what would it feel like if we could sense radiation the way we feel warmth or smell rain? Would a weakening magnetosphere taste metallic or hum faintly in your bones? The changes aren't catastrophic yet. But in certain regions like the South Atlantic anomaly, the field dips to less than half its normal strength, around 25 microteslas instead of 50 or more. It's still enough to shield life on the surface from most harmful cosmic rays, but high above in the paths where satellites glide, the effect is more pronounced. Instruments experience more glitches, electronics hiccup under the extra radiation. Engineers quietly adjust orbit's power down sensitive components when passing through weaker zones. You imagine the magnetosphere as a great guardian, tall and cloaked, holding a shield high against the sun's constant stream of charged arrows. Normally the shield deflects almost all of them, but during a reversal, the guardian becomes tired, the shield lowering slightly, letting a few more arrows glance past. Not enough to wound the world, but enough for the guardian to notice. On the surface, you'd never guess from sight alone. The fields, forests, and cities carry on as usual. People make coffee, drive to work, scroll through their screens. Yet above them, cosmic particles are threading down through the upper atmosphere in places they've never reached in living memory. In the polar regions, this is normal, but now the rules are changing. Scientists monitoring the field speak in soft numbers. The global average strength has decreased by about 10% in the last century. A reversal could see it drop to a third of its normal value for thousands of years. Not enough to strip the atmosphere or doom the biosphere. Earth has survived hundreds of reversals before, but enough to alter how space weather touches our world. In the quiet of the evening, you picture the magnetosphere's invisible lines curling and weaving like strands of silk in a slow current. Some lines snap into new shapes, others drift apart. You can't hear them, but you sense they're singing a different song now, one that hasn't been heard for hundreds of thousands of years. And as you lie back to watch the stars, you wonder if the shield falters, even for a while. What new stories will the sun write in our skies? You hear them before you see them, a flurry of wings overhead, a shifting chorus of chirps and calls that seem oddly uncertain. A flock of birds is circling, not in their usual purposeful V-shape, but in a ragged looping pattern, as if debating where to go. These are long-distance migrants, the kind that travel thousands of kilometers without maps or human-made instruments. They carry their own compasses inside their bodies, tiny, delicate sensors attuned to Earth's magnetic field. It's called magnetoreception, and for them, it's as natural as breathing. The field lines that humans can't see are for these birds like glowing threads stretched across the globe, invisible highways leading them home. But now those highways are changing. Where the lines once ran straight to a known destination, they now curve unexpectedly, bending toward a new and unfamiliar north. The birds circle again, their wings catching the light, trying to reorient. You might ask yourself, if a creature's entire map is redrawn without warning, how do they find their way? Do they trust their other senses? Smell, sight, the feel of wind on their feathers, or keep chasing the ghost of the map they once knew? It's not just birds. Sea turtles hatched on a beach they've never seen before, crawl into the ocean, and imprint on the magnetic signature of that exact location. Decades later, they return to that same stretch of sand to lay their own eggs, guided by that memory of the Earth's field. Salmon in northern rivers do the same, navigating by magnetic cues stored since they were fry. Even some bacteria orient themselves with microscopic crystals of magnetite inside their cells, like nature's tiniest compass needles. When the poles wander, these natural navigators face an unexpected challenge. Their internal maps no longer match the reality outside. A sea turtle returning to her birthplace might find herself swimming hundreds of kilometers off course before she realizes the error. A whale's migration path could shift, nudging it closer to shore or into unfamiliar waters. Scientists have seen hints of this before. In past magnetic fluctuations, bird migration routes have drifted, causing temporary declines in survival rates until the animals adapt. Some do so quickly, learning new landmarks or adjusting their internal settings. Others struggle, especially species that rely almost entirely on magnetic cues. You imagine a young bird following an invisible ribbon in the sky. In its mind, the path leads straight to a feeding ground where insects swarm in the millions. But the ribbon twists, now leading it into empty skies. Below, the land and water are the same as they've always been, but to the bird, the world feels quietly rewritten. Perhaps the most haunting thought is this: you would never notice unless you happened to watch them long enough, unless you cared enough to ask why their shapes in the sky look different this year. The reversal leaves few traces on the ground, but in the air and the sea, in the instincts of millions of creatures, it redraws the map of life itself. And as the flock above you finally makes a decision and drifts off toward the horizon, you can't help but wonder, in the great story of Earth's poles, are humans the only ones who will read the ending in books, while everyone else learns it by flight, fin, or instinct? Far below the restless flocks and shimmering skies lies a slower, quieter record of the pole's wandering one, written not in feathers or light, but in stone. You find yourself walking along a rocky shoreline at low tide, where dark, fine-grained basalt peeks through the sand. The surface glistens with seawater, and if you had the right instruments, you could read in these rocks the story of a magnetic field long gone. The ocean floor is like a vast archive of the planet's magnetic moods. Every time molten lava seeps up at a mid-ocean ridge and cools, tiny crystals of magnetite inside the basalt align with the magnetic field as it is at that exact moment. It's like they're taking a tiny, precise compass, reading and freezing it in place forever. Once the rock solidifies, that alignment doesn't change. The crystal grains keep pointing in that ancient direction, even if the poles wander thousands of kilometers away. You might ask yourself, what other secrets lie locked in the minerals beneath our feet, waiting for someone to learn the language to read them? And how far back could such a magnetic diary stretch? In some places, these frozen compass readings are perfectly ordered, forming symmetrical stripes on either side of a mid-ocean ridge. These magnetic stripes, some pointing north, others south, are like the barcode of Earth's history, each band marking a time when the field was oriented one way or the other. Together they show a pattern of reversals stretching back tens of millions of years. If you could dive down along a ridge, you'd see these stripes running for hundreds of kilometers, alternating black and white in the language of geophysics. A paleomagnetist, a scientist who studies these ancient magnetic clues, might run a sensitive magnetometer over the seafloor and watch the needle swing first, one way then the other, tracing the zebra pattern of reversals. But the ocean isn't the only keeper of these memories. Lava flows on land, preserve the same magnetic whispers. Ancient clay deposits can, too, their iron-rich grains settling in alignment with the field before the sediments harden into stone. Some of these records are astonishingly old, over 3 billion years in certain cratons, telling us that Earth has had a magnetic field for most of its history. The most famous of these stone memories might be the sequence found in the basalt of the mid-Atlantic ridge, where scientists first confirmed that the seafloor was spreading and the poles had flipped many times before. Without those magnetic clues, plate tectonics itself might have taken longer to understand. You run your hand over the rough basalt on the shore. To you, it's just rock, cool, solid, and silent. But to someone with the right tools, it's a page in a book, a moment when the molten heart of the earth whispered north is here, and the rock listened. And somewhere in the deep ocean right now, fresh lava is cooling its tiny crystals, aligning with today's magnetic field. They don't know that in a few thousand years, today's north will be tomorrow's south. They're just doing what they've always done, quietly writing history, one cooling grain at a time. Night falls again, and this time you're not alone in your quiet vigil. People have gathered in a grassy park on the edge of the city, their faces tilted upward in wonder. Far above the sky is spilling with light, not from street lamps or fireworks, but from auroras that have wandered far from their usual polar homes. Here, hundreds of kilometers from either pole, the horizon shimmers with a slow, graceful undulation. Curtains of green sway like underwater kelp forests, threaded with streaks of rose and violet. You can see the colors even from the heart of the city, where normally the sky glow from neon signs drowns out the stars. Now the auroras are bright enough to outshine the urban haze. Children lie on picnic blankets, pointing at shapes in the light. Someone swears they can see a dragon forming in the folds of green. A few photographers are set up with tripods, their cameras clicking softly every few seconds, trying to catch the sky mid-dance. You might ask yourself, how many generations have gone without seeing this spectacle in these latitudes? And if these auroras stay for centuries, will future city skylines always share the heavens with curtains of light? The cause is the same invisible shift you've been following, the pole's wandering path, changing the way Earth funnels the sun's charged particles. Where the magnetosphere is weakened or bent, those particles dive into the atmosphere in places they never did before. They collide with oxygen and nitrogen, shaking them into releasing photons green from high-altitude oxygen, deep crimson from the lower layers, and purples from nitrogen's glow. You picture the aurora as a painter who has been told to work only on a small canvas at the top of the world. Now the canvas has been stretched wider, and the painter is spilling color far beyond the frame. There's a strange intimacy to seeing this in a city. In the polar regions, auroras are common enough to be background magic, something people love but expect. Here the lights are startling, a reminder that the sky is not always a constant ceiling. The office towers look smaller against them, as though the city itself has stepped into an older, wilder world. Some people pull out compasses to check if the strange sky means the rumors are true. The needles wobble slightly before finding a new north. Others just lean against each other and watch in silence, letting the slow rhythm of the lights quiet their breathing. You realize that for many here, this is the first time they've seen the solar wind touch their home so directly. It's both a gift and a whisper of something larger happening, something no one here can stop, only witness. As the night deepens, the lights begin to fade, retreating toward the horizon. Conversations pick up again, the city noises return. But everyone leaves with a piece of the sky stored away in their memory, glowing faintly even as the real thing disappears. And you wonder when the poles finally complete their switch, will the auroras still come this far? Or will they drift back to the ends of the earth like homesick travelers? High above the shimmering skies and wandering compasses, a quieter drama is unfolding, not in forests or oceans, but in the vacuum of space. There, fragile human-made machines glide along their orbits, each one a small bead of metal and electronics riding inside Earth's protective bubble. Normally, the magnetosphere shields them from the brunt of the sun's charged particles. But during a pole reversal, that shield grows uneven and in certain regions thin. The South Atlantic anomaly, that sprawling weak spot hovering over parts of South America and the Southern Atlantic, is one of the most notorious. Satellites passing through it are like travelers stepping briefly out from under an umbrella into a sudden rain. Inside a low Earth orbit satellite, you'd see racks of instruments, each one carefully shielded in metal casings. These are delicate sensors, built to measure climate patterns, relay GPS signals, beam phone calls across oceans. But as the field above weakens, more high-energy particles slip through, flickering across their circuits like ghostly fingerprints. You might ask yourself, how do you protect something when the very sky above is letting more of the storm through? Can you make a satellite sleep through danger the way a bird might huddle in bad weather? Engineers have learned to do something similar. When a satellite enters a region like the South Atlantic anomaly, non-essential systems can be powered down, reducing the risk of damage. Astronauts aboard the International Space Station, which also passes through that zone, sometimes pause sensitive experiments for the same reason. Even the Hubble Space Telescope takes short breaks when passing through, like an eye closing against a bright flash. The risk isn't only in sudden failures. Over time, increased exposure to cosmic radiation can degrade solar panels, cause bit flips in onboard computers, and subtly age satellites faster than planned. During a prolonged weakening of the field, these problems could multiply, forcing space agencies to build hardier craft or accept shorter lifespans. From the ground, you wouldn't see any of this. The satellites would still streak overhead, tiny moving points against the stars. The ISS would still shine like a slow meteor, crossing from horizon to horizon. But behind those steady lights, invisible battles would be fought against particles born in the sun's core, traveling for days across space and slipping through Earth's thinning guard. In your mind, you picture the magnetosphere as a great transparent net. Normally, it's taut, catching most of what the sun throws our way. Now small holes have opened. Satellites pass through those holes like fish in a shallower stream, exposed for just long enough to feel the difference. And somewhere far above you tonight, one of those satellites is quietly switching into safe mode, waiting out its brief passage through a patch of sky that has grown less friendly in this age of wandering poles. You find yourself holding a piece of cooled lava in your hands, dark, heavy, flecked with tiny crystals that catch the light. To most, it's just a rock, but to a geologist, it's a postcard from a time when the world's magnetic field pointed in the opposite direction. Deep inside this basalt are grains of magnetite, each one a microscopic compass needle. When the lava was molten, these grains floated freely, tumbling in the fiery liquid. But as it cooled, they froze in place, locking themselves to the magnetic field's orientation at that exact moment. And if that moment happened during a pole reversal, they now point south instead of north, a permanent record of a world flipped upside down, magnetically speaking. You might ask yourself, how many such stones have been whispering this story for millions of years, their message hidden until someone thought to listen? The story of ancient pole reversals isn't told in a single rock, but in patterns. Across the globe, scientists have collected samples from lava flows, ocean sediments, and even ancient pottery. Yes, pottery. When clay is fired in a kiln, its iron-bearing minerals align with the field just like lava cooling. That means a pot made thousands of years ago can carry a faint baked-in memory of Earth's magnetic state. But the real treasure trove lies in long sequences, stacks of lava flows piled over millennia, each one preserving a different snapshot of the field. In places like Hawaii, Iceland, and the Afar region of Ethiopia, these layers form a magnetic timeline that stretches back hundreds of thousands of years. The evidence shows that reversals are not clockwork events. Sometimes they happen every few 100,000 years. Sometimes millions of years pass between flips. And the transition can be slow or fast, a few thousand years, or in rare cases perhaps under a century. In each reversal, the field weakens, wavers, and eventually reorients. For a time, multiple north and south poles may exist, at once scattered irregularly across the globe before settling into the new order. It's like watching a compass needle spin in slow motion, pausing then pointing somewhere entirely different. If you could walk back through time and witness one of these ancient flips, you'd see little change in the landscape. No sudden cataclysm, no apocalyptic fire. But if you looked at the sky during periods of weakened field strength, auroras would spill toward the equator. Migrating animals would hesitate in their paths, and above the sun's touch would be just a little stronger. You run your thumb over the rough edges of the basalt in your hand. It's cool now, but it once glowed at over 1,000 degrees Celsius, fresh from the Earth's mantle. It cooled in air, touched by the same magnetic field you live under, though back then the names North and South meant the opposite of what they do now. Somewhere in the deep rock layers of the world, today's cooling lava will hold the story of this reversal, waiting patiently for someone in a far-off future to read it. The air feels different, though you can't quite explain why. It isn't hotter or colder, wetter or drier, just altered, as if the atmosphere has learned a new rhythm. Weather, after all, is not a separate thing from the rest of Earth's systems. It's woven into the fabric of the planet, and when the magnetic poles wander, the weave can shift in subtle ways. You might ask yourself, can an invisible force, one you can't see or touch, really change the way the wind moves or the rain falls? The truth is, the magnetic field itself doesn't steer clouds or summon storms directly. But it is part of a larger dance between the sun and the atmosphere, a dance that includes charged particles, currents in the ionosphere, and the way energy moves through the upper layers of air. When the field changes shape or strength, those interactions can ripple downward. High above in the thermosphere, increased solar particles, during weaker magnetic shielding, can heat the gases, altering their density. This can subtly influence the jet streams, those narrow rivers of fast-moving air that steer weather systems. Even small changes can shift storm tracks, nudge rainfall patterns, or alter seasonal timing. Imagine the atmosphere as a vast mobile hanging from the ceiling. Normally, the magnetosphere keeps the sun's energy balanced across its strings. But during a reversal, the weight shifts. Some parts sway more than usual, others fall still. Scientists studying paleoclimate records have found hints that certain reversals coincided with changes in regional climates. In some cases, there's evidence of stronger winds in the tropics or shifts in monsoon patterns. In others, they see spikes in atmospheric carbon-14 created when cosmic rays strike nitrogen atoms, suggesting that more high-energy particles were reaching the atmosphere. Those spikes sometimes match periods of unusual weather in ice core and sediment records. To the people living through such times, these changes would feel local, and immediate. A rainy season might start later than usual. A familiar wind could blow from an unfamiliar direction. Farmers might look at the sky and decide to plant earlier or later, guided by instinct and experience. No one would point to the pole's movement as the cause, but the connection would be there, hidden in the chain of cause and effect. You picture a small fishing village on the coast centuries ago. The elders notice that storms are coming in strange patterns, arriving from the wrong quarter of the horizon. They weave this into their weather lore, perhaps giving it a name, the wind that forgets, without ever knowing that deep inside the earth, molten iron is the true storyteller. Here and now the changes are gentler, but no less real. A winter storm takes a path farther south than expected. Clouds gather in sheets above, places that rarely see them. The wind at night carries a different scent, as if it's been on a new journey before reaching you. And you realize that the pole's wandering isn't just a story written in stone or the sky, it's etched in the moving air, in the quiet shift of seasons, in the breath of the planet itself. Beneath your feet, the ocean is not still, not even for a heartbeat. It breathes and shifts, carrying heat salt and life in great slow rivers that span the globe. These currents, the conveyor belts of the sea, are driven by a mix of winds, temperature differences, and the subtle push and pull of Earth's rotation. But you might ask yourself, if the planet's magnetic poles swap places, can that invisible rearrangement ripple into the waters themselves? Directly, the magnetic flip doesn't shove the sea around like a giant hand, but the connections are tangled. The same changes in atmospheric circulation that nudge winds in new directions can also alter the ocean's surface currents. And below the waves, another layer of influence lurks, the ocean's own faint electric currents. Seawater is salty, and salt makes it conductive. As the planet's magnetic field moves and reshapes, it can change how the electrically charged particles in seawater flow. This doesn't send dramatic tidal waves crashing across continents, but it can subtly shift how certain currents interact, especially in polar waters where the field is strongest. Picture the Antarctic circumpolar current, the only one that loops endlessly around the globe without hitting land. It's like a silver belt cinching the southern oceans tight. If wind belts above it shift just a little, the current can speed up or slow down, tugging on climate far beyond Antarctica. A faster current might pull up more cold, nutrient-rich water from the deep feeding blooms of plankton that turn the sea a brighter green. A slower current might let warmth pool in ways it never has before. In the North Atlantic, the story gets even more delicate. Here, the Atlantic meridional overturning circulation acts like the ocean's central heating system, carrying warm surface water north, where it cools, sinks, and returns southward in the depths. Slight changes in storm tracks or temperature gradients. Possible side effects of altered atmospheric patterns could tilt the balance of this system. And then there's the quieter player, the Earth's electric signals picked up by marine life. Many species, from sea turtles to certain fish, can sense magnetic fields using them like a built-in compass. During a reversal, when the field weakens and shifts, migration routes might blur. A turtle leaving a nesting beach might swim a little too far east or west before finding the open ocean's invisible roads. Imagine watching from a cliff above a broad bay. You see a school of shimmering fish breaking the surface, turning in loose, uncertain spirals instead of their usual tight, decisive arcs. The tide still comes and goes, the waves still crash, but the water's mood feels unsure, as if it's listening to a different kind of whisper from the deep. So while the ocean won't leap in panic at the pole's new orientation, it will hum a slightly different song. One you might notice in the color of the water, the arrival time of certain fish, or the way waves carry themselves to shore. The Earth's magnetic heartbeat is felt here too, just in the slow, patient language of the sea. You tilt your head back and imagine the sky as a vast, breathing canvas, one that changes not only with the time of day, but with the slow dance of invisible forces surrounding the planet. The atmosphere is not a passive blanket. It's a restless painter, layering clouds, light, and air currents into living art. But when the poles begin to trade places, the very way this painter works could change. The magnetic field, though invisible, guides high-energy particles streaming from the sun. Normally, the poles act like funnels, pulling those particles toward the magnetic north and south, where they dive into the atmosphere and create auroras. But in a reversal, those funnels move, sometimes splintering into multiple points or wandering into mid-latitudes. You might one night see shimmering curtains of green and violet over the tropics, and wonder if the sky has decided to throw a surprise party. The weakening of the field during the transition allows more solar particles to slip into the upper atmosphere. That means more ionization in places where it's not usually strong. Think of the upper layers of air suddenly becoming a little more electric, like a charged hush before a thunderstorm, but stretched across continents. And you might ask yourself, could this shift change the way weather forms? In some ways, yes. The jet stream, a high-altitude river of fast-moving air, is sensitive to temperature differences between the equator and the poles. If the pole's magnetic realignment alters how solar energy is absorbed in different regions, the jet stream's path might wobble more than usual. Wobbles mean surprises, a sudden plunge of polar air deep into warm latitudes, or a streak of summer heat racing northward in spring. Then there's the dance of clouds. With more particles entering the atmosphere, there could be changes in cloud nucleation, the birth of clouds around tiny seeds of dust ice or charged molecules. Some studies suggest that in certain conditions, more ionization can encourage cloud formation, especially in the lower atmosphere. Imagine the tropics wearing a gauzier veil of clouds for days longer than they used to, softening the sun's glare and dimming the turquoise sea below. And think of storms. If patterns shift, cyclone tracks could bend in unexpected ways. A storm that once would have curved harmlessly out to sea might instead sweep over islands or hug a coastline, carrying rain to places that are not ready for it. Farmers, fishers, and even migratory birds would notice before the scientists confirmed it, because the rhythms they've trusted for generations would feel slightly offbeat. The atmosphere personified becomes a moodier artist during this transition, bold in some places, hesitant in others. It might drape the equator in ribbons of lightning-streaked clouds while leaving polar skies strangely bare. Or it might draw auroras so wide and bright that they cast shadows on the snow. If you were to stand outside one of these nights, the air cool against your cheeks, you might feel that the planet is speaking more directly, not in the soft, indirect language of seasonal change, but in a louder, more improvisational tone. And you might wonder, is this a brief creative phase, or is the sky telling you it has adopted a new style altogether? You picture the ocean as a slow-breathing giant, its chest rising and falling with the pull of the moon, the push of the wind, and the quiet churn of deep currents. Normally, those currents have a dependable rhythm, a conveyor belt moving warm and cold water around the planet. But in the middle of a pole reversal, the giant's breath might change tempo. This isn't because the magnetic field controls the tides. The moon and the sun still own that domain, but because changes in the atmosphere ripple downward. Shifts in wind patterns alter the surface currents, and surface changes can over months and years disturb the deep ocean's heartbeat. If storm belts drift or intensify in new regions, they can push warm surface water farther into polar seas or drag cold water into places that rarely see it. The magnetic field also protects the ocean indirectly by shielding Earth's climate system. When it weakens, more solar and cosmic radiation can reach the upper atmosphere, subtly changing how much heat the oceans absorb. Even a small difference in surface heating can nudge currents off their usual paths. Imagine the Gulf Stream, a great warm river in the Atlantic bending slightly east or west. That little kink could mean wetter winters in one country and drier summers in another. Then there's the life inside this breathing giant. Plankton, the ocean's invisible forests, rely on stable layers of warm and cold water to bloom in the right season. If winds shift and mix those layers at unusual times, plankton might surge early or starve later. And because plankton feed everything from tiny fish to massive whales, a single mistimed bloom could echo through the entire food chain. In the polar seas, where icy calm usually dominates, new storm tracks could stir the surface, breaking up sea ice earlier than expected. Seals might haul out onto shrinking platforms, penguins might adjust their hunting routes, and polar bears, those wandering kings of the Arctic, could find their hunting season shorter by weeks. The ocean itself feels like it's listening to a new conductor, one who favors unexpected pauses and sudden crescendos. You might walk along a coast you've known since childhood and find the tide pools richer with life in some seasons, emptier in others. Fishermen might shake their heads at new species caught in their nets, fish that seem like lost travelers guided by a map the sea has redrawn. And in the deep, where sunlight never reaches and strange creatures glow softly in eternal darkness, even there the change is felt. The great thermohaline circulation, driven by differences in temperature and saltiness, is sensitive to what happens above. More melting at the poles adds fresh water, which can slow the sinking of cold, salty currents. Slow the deep currents, and nutrients may no longer rise in the same places, starving some regions and overfeeding others. The question lingers in your mind: if the oceans are the memory of the planet, recording every wind, every season, every melting glacier, what kind of new memory will they keep when the poles have finished their slow trade? And when future generations walk these shores, will the giants still breathe in the same familiar rhythm? Or will they feel in the pull of the waves that they are standing in a different world entirely? High above the clouds, invisible rivers of charged particles flow along the magnetic field lines like glowing threads of silk. Normally, they funnel toward the poles, where they paint the sky in shimmering auroras. But during a pole reversal, those lines twist and meander, and the auroras no longer stay politely at the top and bottom of the planet they wander. You step outside one quiet evening and notice a faint curtain of green stretching overhead. Not toward the north, not toward the south, just overhead. Cities near the equator might find themselves bathed in ghostly light that once belonged only to polar skies. It's beautiful, yes, but also a quiet reminder that the shield is shifting. When the magnetic field weakens, more solar wind can enter the upper atmosphere, injecting extra energy into its layers. The ionosphere, a high, delicate skin of charged particles, swells and ripples. Communications signals, the kind satellites send to guide ships, planes, and even your phone, might bend strangely or scatter. Air traffic controllers might notice little blips in their systems. Navigators might need backup plans that don't rely on magnetism at all. The sky's colors would also change subtly. Auroras might gain streaks of deep red more often, as oxygen atoms higher in the atmosphere get excited by incoming particles. Blue and purple hues from excited nitrogen could flare unexpectedly. Imagine walking home under a violet sheen sky, unsure whether to stare or quietly close your eyes and feel the hum of the planet's magnetic pulse in your bones. Of course, the auroras are only the visible part of the story. Invisible radiation riding along with the solar wind would reach farther into the atmosphere than usual. Most of it is still absorbed high above where planes fly, but in intense solar storms, bursts could dip low enough to cause power grids to flicker or GPS to falter for a few hours. You might find yourself watching the news as scientists talk about geomagnetic storms, more often their voices calm but edged with focus. Animals that read the sky's whispers, like birds, bats, and even certain insects might have their compasses confused. A migrating goose might bank sharply, mid-flight, following a path that no longer lines up with the stars it learned as a hatchling. The skies could briefly fill with flocks circling or scattering in unfamiliar patterns, like a living feathered question mark. And there's an odd, human side to all this. People might begin planning nighttime gatherings, not just for meteor showers, but for these wandering auroras. Photographers could set up tripods on tropical beaches, waiting to catch ribbons of green and red over palm trees. Children might lie on rooftops in cities wide-eyed as they watch the heavens change from quiet black to a glowing ocean of color. As you imagine this, you realize the atmosphere itself feels almost like a stage, and the magnetic field normally, a disciplined stagehand has decided to improvise the lighting. The show is unpredictable, sometimes faint, sometimes breathtaking, always a reminder that even the most reliable systems in nature have moments of restless creativity. And somewhere between the beauty and the disruption lies a humbling truth. The atmosphere is not a still ceiling above us, but a living, shifting canvas painted daily by the invisible forces of our planet's magnetic heart. Down in the oceans, where light fades into a deep blue twilight, another quiet confusion stirs. Many marine animals, from tiny plankton to massive whales, sense the magnetic field and use it as a map. They can see it in ways we can't, detecting faint magnetic lines the way you might feel the subtle tug of a current while swimming. Now imagine what happens when those lines shift. The ocean's magnetic landmarks, invisible highways in the saltwater, begin to bend and drift. A young sea turtle born on a tropical beach and programmed to migrate thousands of kilometers to feeding grounds might suddenly find that its internal compass points to a new puzzling direction. It swims with confidence, but ends up somewhere entirely unexpected. Some creatures rely on a combination of cues: the sun's angle, the star's water temperature, and the Earth's magnetism. During a reversal, those other cues still work, but the magnetic piece becomes scrambled, like replacing one note in a familiar melody with a discordant sound. A pod of dolphins might veer off their usual course by hundreds of kilometers before realizing their mistake. Schools of fish could bunch up in unfamiliar areas, confusing fishermen and predators alike. Humans might notice subtler signs first: unusual fishing reports, unexpected sightings of certain whales or sharks far from their normal routes. Marine biologists would scramble to update maps and tracking data, while coastal communities might suddenly find new species appearing near their shores. In the deep ocean, even plankton might drift differently, shifting the very foundation of the food chain. Since plankton growth is tied to nutrient-rich currents, and those currents can be subtly influenced by the Earth's rotation and magnetic layout, the changes could ripple upward, affecting everything from anchovies to seabirds. Picture the ocean as a great dark ballroom, its dancers following music we cannot hear. The poles switching is like changing the rhythm mid-song. Some dancers keep moving gracefully, adjusting without pause. Others stumble, spin the wrong way, or drift into corners they've never explored. The ocean doesn't stop, but its choreography changes, and new patterns emerge. And perhaps you'd wonder if we humans lived our lives guided by a magnetic sense. As keen as a turtle's, would we feel this change like an itch under the skin? Would we wake one morning with an unshakable urge to travel somewhere entirely new, drawn by a compass we can't see? As the poles wander, the sea itself becomes an experimental map, and its travelers finned, flippered, or tentacled are both explorers and the explored. And you, listening in the quiet, can almost hear the slow turning of that invisible compass beneath the waves. Above the surface, in the great expanse of sky, creatures with wings feel the shifting just as keenly as those with fins. Birds especially, the long-distance migrants, are among the most skilled navigators on Earth. You might picture them as tiny feathered pilots carrying invisible maps imprinted into their minds before they ever take their first long flight. These maps aren't just visual, they're magnetic. When the poles begin to switch, the map itself redraws mid-journey. Imagine a flock of Arctic terns flying a migration route of over 70,000 kilometers each year, their path curving smoothly from pole to pole. Now a gradual but persistent skew creeps into their compass sense. That perfect line of travel bends ever so slightly enough to take them hundreds of kilometers off course by the end of their migration. Some arrive in strange wetlands they've never seen. Others find themselves circling the sea, confused as if the landmarks in their minds have been erased. Homely pigeons famous for their uncanny homing instinct might find their performance faltering. Instead of arrowing directly home, they spiral outward, stopping to rest in unfamiliar towns. Researchers watching from the ground would notice statistical shifts, a greater spread in arrival times, more birds lost entirely. And the cause would lie in the sky above them, woven into invisible lines of force. You might ask yourself, if you were one of these creatures, would you trust your old path, clinging to a fading memory of the map? Or would you let yourself drift, with the new pull discovering where it leads? Even insects aren't spared. Monarch butterflies, those delicate migrants whose wings beat against the wind for thousands of kilometers, sense the Earth's magnetism too. If the cues waver, they may end up in patches of forest far from their ancestral overwintering grounds. That misstep could ripple through entire ecosystems, flowers left unpollinated, predators missing a seasonal feast. Some birds adjust by blending cues, the position of the sun, the smell of the land below, or even the rumble of familiar ocean currents beneath their flight paths. But others, especially the youngest migrants, may falter. They are like children, given a storybook with half the pages out of order. The plot still makes sense in places, but the journey feels strange, unsettling. In time, species would adapt. Evolution favors the flexible navigator, the one who notices a shift and quietly alters course. But during the change, the skies themselves become a web of crossed paths, missed landings, and unexpected meetings. Birds from distant continents might find themselves side by side in the same estuary, strangers sharing a rest stop neither had planned for. If you could stand in a meadow during this time and listen closely, you might imagine hearing their voices in a different key, not the crisp confidence of well-worn routes, but the soft uncertainty of travelers feeling their way through an unfamiliar map of the air. And high above the sky keeps its secrets, watching them all from horizon to horizon. While creatures of the sky are redrawing their invisible maps, you find yourself drifting into the realm of human memory, deep time, the kind that exists in stone, ice, and fossils. The story of past pole reversals is written in layers, almost like the rings of a tree, but the pages here are iron-rich minerals cooled from ancient lava flows or settled gently on the seabed over millions of years. Picture yourself walking along a cliff face made of hardened volcanic rock. Some layers sparkle faintly in the fading light, flecks of magnetite glinting like scattered constellations frozen in stone. When molten, these minerals acted like tiny compass needles, swiveling to align with Earth's magnetic field before solidifying forever. The result is a perfect snapshot of the direction of north at the moment they cooled. But as you trace the strata upward, you notice something strange. In one layer, the magnetic pull points roughly where today's south would be. Just above it, the direction flips back. Then it flips again. Like the pulse of a sleeping planet, these reversals mark epochs of change. Scientists call this magnetic striping, especially when seen on the ocean floor. Imagine two conveyor belts of rock slowly moving away from a mid-ocean ridge, each new strip cooling and locking in the planet's magnetic orientation at that time. Over tens of millions of years, the pattern looks like a barcode, light, dark each stripe, representing a chapter when the poles either matched our current layout or sat reversed. And here's a thought: if the seafloor is the book, then these stripes are like bookmarks placed there by the planet itself to remember its own wandering compass. You might ask yourself, how many times has the planet completely switched its mind about which way is north? The answer is staggering. Over the last 20 million years alone, it's happened more than 70 times. Sometimes the flips were hundreds of thousands of years apart. Sometimes they came in bursts almost impatiently, one after another. Ice cores tell their own version of the tale. Buried deep in Greenland and Antarctica are frozen layers that whisper about climate shifts tied to changes in the magnetic field. Trapped within them are tiny air bubbles, each a time capsule of ancient atmosphere. In periods when the magnetic field weakened, more cosmic rays streamed into the upper atmosphere, sparking chemical changes that are still visible today. Even the sediments at the bottom of lakes carry the memory. In quiet waters, fine particles drift down year after year, stacking in delicate, undisturbed layers. Mixed among the clay and organic matter are grains of magnetic minerals that settled aligned to the prevailing field. Drill down with care, and the core you pull up becomes a timeline of the field's moods, steady wavering, and sometimes, suddenly, inverted. It's humbling to think that every one of these records is silent until we learn how to read it. The planet has been keeping a diary for billions of years, but in a script only a handful of patient eyes can decipher. And even then, the story is incomplete. Missing pages, faded ink, and twists that leave us wondering what the ending might be. Somewhere in all that stone, ice, and sediment, your own era is just a thin sliver, barely a breath in geological time. If the poles do decide to wander again in your lifetime, the record will be written too, layer upon layer, waiting for curious eyes millions of years from now. And perhaps they'll wonder about you, just as you now wonder about the creatures and landscapes that lived through the last great switch. Now the air feels even softer around you, as though the story itself is slowing, making space for a gentler pace. The present moment drifts in like a leaf settling on still water. You imagine Earth as it is now, a steady heartbeat beneath your feet, magnetic field, flowing like a slow, invisible wind around the planet, catching solar particles and guiding them harmlessly away. You let yourself picture that shield as a great, luminous dome shimmering with unseen colors. Even though we cannot see it, it's always there, cradling oceans, mountains, forests, and every small, fragile life beneath. At its edges, where the field lines dip towards the poles, ribbons of aurora swirl and dance quiet fireworks in the thin, cold air. They are the most beautiful evidence that this invisible guardian is hard at work. Perhaps the most soothing truth is that while reversals are a part of Earth's rhythm, they unfold over thousands of years. The shift is not a sudden toppling, but a slow, graceful turning, like a dancer, changing direction so subtly you might not notice at first. Humanity has not yet lived through a full reversal in recorded history, and when it comes, life will adapt just as it has so many times before. The magnetic field might grow weaker for a while, its protective veil becoming more gauzy, but it will not vanish. The compass may point in strange directions for a time, yet the sun will still rise, the tides will still breathe in and out, and the seasons will still roll onward. You might ask yourself, if the world has worn so many different faces, if North and South have traded places again and again, what does permanent really mean? Perhaps the only constant is change, and the comfort lies in knowing that change itself is natural, ancient, and deeply familiar to the planet. So you picture the Earth as a slow-turning sphere in the dark, swaddled in its magnetic cocoon. Time moves forward, poles wander, life continues. Somewhere deep in the future, another curious mind may sit, listening, imagining how the world once looked when the poles switched place, and smile at the thought that they are part of the same long, unbroken story. The air is warm, now heavy with quiet. Your eyelids feel slow, your breath steady. The images blur, auroras becoming waves, waves becoming hills, hills becoming the steady rise and fall of your own breathing. You let the planet's ancient pulse carry you toward stillness. If you've enjoyed this journey, I'd be quietly grateful if you'd give this video a like or tap that subscribe button for more peaceful explorations with the Sleepy Scientist. It helps more than you might imagine. And before you drift off, I'd still love to know, where in the world are you listening? From what time it is there? Leave a comment if you're feeling cozy enough to share. It's always a quiet joy to see this sleepy little community ripple across time zones and continents. Good night.